this would be something else, right? So, yeah, exactly. But the cone that's on the sheet I gave you this today is not a single cone, it's a double cone. What was the quadratic surface presentation of the cone? It's what? Right, let's be lazy. Let's be a circular cone. That's what we have here. It's that. Right. So am I being honest with you? Is this really a cone? How can we check it? How can we compare this way of thinking with what's on the sheet? How do we go between these worlds? X is equal to what? Rho cosine theta sine phi naught, right? Y is rho sine theta sine phi naught. Z is rho cosine phi naught. How can I tell if these parameterize the green equation? I need to give it a name. What? Ice cream? Okay. Now you're making me hungry. Okay. Do these parameterize ice cream? This is a very silly class. All right. I'll take it though. So if somebody gives you, if you go to the parameterization store and they sell you a parameterization for the level surface, right? If you plug in the parameterization into the equation for the level surface and it doesn't satisfy the equation, you should take it back. So we can plug these in to here and see if it actually works. Does it work? I don't know. So we got rho cosine theta sine phi naught quantity squared. That's my x squared, right? Rho sine theta sine phi naught quantity squared minus what? Minus rho cosine phi naught quantity squared. What's this work out to? Is there a rho squared everywhere? Yeah, we got rho squared. I'm worried. It doesn't look to me like I'm going to get 0. Huh. Yeah. Well, yeah, I mean, right. I got cosine squared theta, sine squared phi naught, right? Plus sine squared theta, sine squared phi naught, minus cosine squared phi naught, right? Of course, these guys collapse down to what? Sine squared phi naught, right? Because you get sine squared plus cosine squared is 1. So we have rho squared sine squared phi naught minus cosine squared phi naught. What kind of cone are we looking at on the formula sheet? Cone of what angle? If you look at this cone, right, you can look at traces. In particular, you can look at the trace of the cone in the YZ plane. What's that? X equals to 0, right? What happens when you put x equal to 0? You get y squared minus z squared equals to 0 for the cone, right? You get the lines, y is plus or minus z. In other words, what I'm trying to tell you is the cone on your formula sheet that I gave you to start a class is not just any old cone, it's the 45-degree cone. it has lines of slope 1 on its edges if you look at the coordinate planes. So what happens to sine and cosine of 45 degrees? They're what? They're equal. So in the case of 45 degrees, this is 0. I know, I was worried too. But the bottom line is, if you had a cone which wasn't 45 degrees, like if you had a 30-degree cone, the Cartesian equation for it, it's not so nice. But from this, I could figure out what it was. See, I could work backwards from here now that I have complete control over a cone of any angle with these formulas. If I want to work backwards and find out what's the Cartesian equation for it, I could do such if I wanted to. I don't know. It seemed like a good homework question. But I think I thought of it now, not when I wrote your homework, so you're probably safe. But if you keep talking to me about it, there's another place where I ask questions. So any questions about this? What would the equation of a plane look like in spherical coordinates? Or what does the equation of a cylinder look like in spherical coordinates? You're like, how about a plane in spherical coordinates? A plane is what? AX plus BY plus CZ equals to D for specific constants A, B, C, D. Right? This is what we call the pointless equation for the plane. How do you find the equation for a plane in spherical coordinates? Here it is. A rho cosine theta sine phi plus B rho sine theta sine phi plus C rho cosine phi equals to D. So if you're working in spherical coordinates and you come across such an equation, you're like, a plane! You should say, that's stupid. That would be right. That is stupid. We don't use spherical coordinates to describe planes because planes are not something that are natural in spherical coordinates, right? A plane, we use Cartesian coordinates for, right? But a sphere is something we should really give some thought. Maybe we should use spherical coordinates to describe a sphere. Because a sphere in spherical coordinates is rho equals to that number, the radius. Done. Game over. A sphere in Cartesian coordinates is x squared plus y squared plus z squared equals to that number squared, which is kind of a pain. It's a lot of a pain when we get to integration. If you do the same integral in spherical coordinates, it would be way easier. How about a cylinder? Sometimes there are problems which are necessarily involving both spherical and cylindrical symmetry. So you just kind of have to fall on the sword either one side or the other. So sometimes it's important to know about this. If I have a cylinder x squared plus y squared equals to r squared, capital R squared, of course this is what? This is r squared. Let me choose something else for the radius. You guys make it whatever you want. We'll do capital A for the radius, okay? A squared. So this gives me r is equal to A, right? I'm supposing that A is positive just for the sake of not being annoying. So there's the equation of the cylinder in cylindrical coordinates. What's the equation of the cylinder in spherical coordinates? This one. So you say rho sine phi is equal to A. So there you go. That's the equation of a cylinder of radius A in spherical coordinates. It's not nice, but it's not too bad. Anyway, I asked you some elementary questions about spherical and cylindrical coordinates on your next mission, just to try to get you started on it. I think it's also, the reason I'm talking about it now is because I talk about parametrizations early. And because I talk about parametrizations early, this is an important tool tool to have in order to write down formulas for parametrizations. That said, I think you guys will all be very, very happy tomorrow when we start calculus, right? Because this algebra and geometry is actually what you guys have a lot more trouble with. When we actually start differentiating, everybody's like, yay! So I shut up. Thank you.